So welcome everyone to the first fully online lecture for random matrices and universality 2. First, let me make a remark about the organizatorial things. So today the lecture will be fully filmed as usual, and starting from next week I'll use Zoom. So all UNIG students that want to be present during the lecture in this virtual, at least virtually, they should go to the Moodle webpage of this course, register there, and then I'll send to you all further details for the lecture next week. And also the exercise session will be handled in the same way via Zoom, starting from next week. Okay, so today we start with the real part of the lecture. So we start with analyzing universality for random matrices, and here we will first prove a statement about bulk universality, so about universality of k-point correlation functions, and there we will use moment matching. We will impose an extra condition on moment matching on the random matrices. So we'll take two Wigner matrices, assume that they have sufficiently high moment matching, and then we will be able to prove that the k-point correlation functions are close to each other when the size of the matrix becomes very large. And so that you have an impression about what this condition of moment matching will be, I first want to introduce this. And we start from two Wigner matrices. One is called H, with entries Hij, and then I'll have a second Wigner matrix H prime, whose entries I will denote by Hij prime. It's also an n times n Wigner matrix. Okay, so we defined what a Wigner matrix is last semester, so I guess you can all go back to this definition. And now the important concept will be that we say what it means that H and H prime match to order little n. Okay, so that's what we will define now. So we will say that H and H prime match to order n if the following holds: if for all I and j that run over the index set of my matrices, and all k and l that start at 0, 1, 2, and can go up to little n, which satisfy that the sum of k and l is at most n, then we require the following condition. We have that expectation of Hij to the k times Hij bar to the l has to be the same as the corresponding expression when the Hij's are replaced by Hij prime. So we take Hij prime to the k and Hij prime bar to the l. Okay, so these are mixed. These are moments of the entries of the matrices H and H prime, and because in general our entries can be complex, we need to take these mixed moments in the sense that we have normal powers and then powers of the complex conjugate. Okay, and now in order to formulate bulk universality, I somewhat have to introduce this notation of k-point intensity measures in the general setup for general Wigner matrix and not just for the GUE. So maybe I go to the next board. So we now introduce some notation. Introduce some for the next theorem. Okay, so now I again have to look at k-point intensity measures, but now I have to distinguish them I have to distinguish which matrix I'm referring to. So now I write rho NH, which refers to the matrix whose eigenvalues we look at. Then the kth intensity measure. And we first start, as usual, with the standard eigenvalue process. And now all eigenvalues are with respect to h. And I define it as follows. If I take a test function f, and then I integrate with respect to this measure, dy1 up to dyk. It's now everything is now in rk. All eigenvalues are real. Then this is defined to be the expectation, again, of the sum, where the star means that I exclude indices to coincide. So this is meant to be the sum over distinct indices f of lambda I1 up to lambda ik. Okay, so that's the same definition as before, except that now we have to make this definition for a general matrix H, and these eigenvalues are meant to be the eigenvalues of H. So maybe I should remark that. So lambda 1 up to lambda n are, of course, the eigenvalues of H. Okay, and this should hold for any measurable and bounded function on Rk. Okay, and maybe not completely obvious, but it's actually quite simple to show it. This rho n hk is a measure, well, maybe I should say positive finite measure on Rk, and this is a homework exercise. We will actually discuss it in the homework session today. Okay, and for your intuition, you should maybe have in mind that rho nk, if I evaluate it at these sets, then this is something like the expected number of k-tuples of eigenvalues in the disjoint sets dy1 up to dyk. So these are subsets of R, and we want to have a k-tuple such that each of the eigenvalues lies in one of those sets. Okay, and then maybe a last property before we rescale the matrix is that if my H, so now I have a general H, so of course the H can have point masses, so the entries of H can have some discrete distributions or even be some Bernoulli, can have some Bernoulli entries. So in general, it's not true that the entries of H are absolutely continuous with respect to the Lebesgue measure, as we had it in the case of GOE or GOE. And in that case, we defined the k-point correlation functions. But now, if my H has a absolutely continuous law, so then this is still true that I can define the k-point correlation function if the entries of H if each entry has a law that is absolutely continuous, with respect to the Lindbergh measure. Then, then this measure rho will also be absolutely continuous. So if I look at this, then I'll find the function P and H k of y1 up to yx, such that this is a density with respect to the Lindbergh measure on Rk. And of course, this will be the k-point correlation function that we are used to. And this was also one homework exercise which we will discuss later. Okay, and now finally we come to the most important definition to state bulk universality. So we need now to look at the local version of this k-point intensity measure, which is rescaled in such a way that that we look at around an energy E, we look at eigenvalues in the vicinity of this this energy. So this is now the most important definition for the next statement. So local k-point intensity measure around E in minus 2, 2. And yeah, note that this again depends on the matrix H. And so I will now write rho n h e k. This is again a measure. Take the alpha k, and then I have this following suggestive notation. So I take the previous measure and then I transform it by centering it at E and rescaling the integration variables following way, such that we go to the space where the eigenvalues have distance 1. So yeah, this is the well, yeah, one should compare it to the rescaled process. So when one rescales the eigenvalue process here, in centering it around E, and then rescaling by n rho of E, which goes then to the local scale. And maybe if you don't quite like this suggestive notation, then I should be precise. So this is the push forward measure. There's some phi E star rho n h k. under the, well, affine linear map phi. Well, I guess I can still squeeze it in here. So phi maps Rn to Rn, and phi n of maybe y1 up to yk looks as follows. It's y1 minus e, so I center it at e, and then I multiply with rho, with n rho of e, and then I do the same yk e n rho of e. So this shifts everything to e and then rescales it in such a way that I'm on the local eigenvalue scale. Okay, and now with the definition of this k-point correlation function, I can finally state this theorem, which we will prove. Well, we start proving it today, and then I guess we can finish it next time. And yeah, as I already said, so this theorem will say that in certain sense, this local k-point intensity measure if I compare two local k-point intensity measures of two Wigner matrices H and H prime, then these measures will be close in a certain sense for large n if H and H prime match to order 4. Okay, so let me state it precisely. So this is theorem 2.2. This is a statement about bulk universality. Well, we call it with 4 matching moments. So the with 4 matching moments refers to the assumption that we will make now. So we introduced it precisely. So I will start with two Wigner matrices H and H prime. And I have to assume that they match up to order 4, or match to order 4, and this match to order 4 was the content of the definition 2.1. And then we have the following statement. So what do I want to do now? Well, I'll leave some space here. So I will test the local k-point intensity measures against the function f. Okay, so I take function evaluated at u1 up to uk, and then I use this to test the local k-point intensity measure for h, the u1, the uk, and then I want to compare this integral with the same integral when I replace h here by h prime. So I have the same integral f u1 up to uk, k-point intensity measure now with respect to h prime, the u1, the uk, and I want this to be small, and what we will actually prove is that this is of order capital N to the minus xi, where xi is one parameter, and the f has to be sufficiently nice. So let me include here the assumptions, or complete the statement. Then there is a xi bigger than 0, such that whenever I fix a k, for any k, for any fixed k in n, I fix an energy E in -2, 2. So that's the bulk, so that's why it's called bulk universality. And a function f, so well, let's maybe say C1 with compact support. We have the following. We have that if we compare these local k-point intensity measures when tested against the function f, then this is of order n to the minus xi for some positive xi. So when n goes to infinity, this clearly goes to 0. Maybe I should make some small remarks. So bulk universality, well, it's called bulk universality because the E lies in -2, 2, which is the bulk of the semicircle. So that's where most of the eigenvalues live. Where when E would be -2 or 2, then this would be the edge, because obviously it's the edge will be the edge of the spectrum, as we showed in the semicircle law last time. And then the implicit constant in this O term here will depend on all these things that we fixed before. Implicit constant, will depend on K, E, and F. And then the rest of this section 2, we will have to invest into proving this statement. So the rest of section 2 is devoted to the proof of theorem 2.2. Okay, and maybe one last remark in just verbally. So this is the kind of universality we meant. So whenever you take two Wigner matrices, which satisfy here some further assumptions, then these measures on the local scale, they are close when n becomes large. And now if you can choose, for example, one of the ensembles to be, let's say the H prime is a Gaussian ensemble, so it's a Gaussian unitary ensemble, then if your H matches this Gaussian unitary ensemble up to order 4, then you know that when n is large, the k-point intensity measures will be close. And furthermore, in the Gaussian unitary case, we even computed this, so we know that this is a sine kernel measure. So we also know that in the limit, when n becomes large here and h matches the GUE up to order 4, then we know that that the k-point intensity measure also converges to this sine kernel measure in a certain in this sense. And that's a very interesting behavior, and it also says that this local eigenvalue process becomes has asymptotically this determinantal structure which we have in the GUE case also for finite n. Okay, and now before going into the proof here, I want to state a version of the central limit theorem and also give its proof, because this will be very instructive for the proof that we will use here to prove this theorem 2.2. And maybe some of you that have looked at the homeworks have already seen it. So this is Lindbergh's proof of the central limit theorem. So this I want to discuss in section 2.1. Lindbergh's proof of the central limit theorem. Okay, and the condition or the strategy we'll use here will be very much tailored to this match to fourth order. Yeah, so this will be very helpful. So the proof of the following result will provide an idea on how to prove Theorem 2.2. Okay, and so Theorem 2.3 will look as follows. So we have a little n, which is in n, and we have n real random variables. So suppose that x1 up to xn are independent. For simplicity, I want to assume now that they are real valued. Random variables that satisfy the following properties. So first of all, we want their second moments to sum up to n, and then we assume that the that the x's are centered. So expectation x ij is 0, and that the third moment is bounded. For all I running from 1 to n, yeah, and k is some constant, Okay, that's positive. Okay, and then what's the statement? Well, we now take a function f. Here for simplicity, we just use that it's C3. And we assume that f and its first three derivatives are all bounded. And then we have the following statement. So I can look. I want to write it. So I want to compute f of the usual combination of the x's in the scaling of the central limit theorem. So I add up x1 up to xn. I divide by root n. I apply f to it, and then I take the expectation. And of course, we would expect that this sum here converges in distribution to a standard normal variable. And the way I want to write it here is that I can subtract the expectation of f of y, and then this will be small. This is of order k f3 prime infinity norm n to the minus 1/2. And y we can choose to be a standard normal variable. So where y is a standard normal random variable. variable. Okay, so and then of course if you take a whole family, a whole sequence of x's, you require this condition pointwise. So for example, you could ask them to be all 1. Then you can conclude from this theorem, if the k and the f here are bounded, that this goes to 0 for n to infinity. So you get that this sum here converges to y in distribution. Okay, and then I think it's helpful to make a few remarks about this statement. And yeah, you see that this is in the same vein here. You test the measure with respect to some function, and then you want to prove that it's small. And well, we will see the y will actually be constructed in such a way that we have Gaussian, that it comes as a sum of Gaussian random variables that match the xi's. Okay, and yeah, first I want to make 2 remarks. So yeah, this remark that I just made about the central limit theorem, that this implies the central limit theorem, I want to write down. Of course, here you have some restriction on the regularity of the f, but you can just approximate a general bounded continuous function by such an f. So that's not a problem. Remarks. So the first one is theorem 2.3 implies the following. It implies that take 1 over root n x1. Now I can put an n here and take these kind of tridiagonal arrays. Then it takes such a sum. This converges to y in distribution. If for each n, this family here, xi, upstairs n, for I running from 1 to n, if this satisfies, this family here satisfies the assumptions of theorem 2.3 for each little n in n, and then yeah, maybe just as a hint, you have to approximate bounded continuous functions. Okay, so that was the first remark. And then the second remark is that, yeah, this is also some kind of universality statement, and even more the central limit theorem. So if you consider, it's in the following sense, because we'll actually see it even a bit better in the proof. So this theorem 2.3 and the central limit theorem, yeah, maybe I should have said that this is, well, something like this is of course called the central limit theorem. Well, it starts here. It's a version of the central limit theorem. There are of course many versions. So these can be considered as a universality statement in the following sense, because they prove that asymptotically two distributions are close, and yeah, in this case they even have they even have some matching moment conditions, because you always assume that the first and second moments somewhat are are matching, or you have to rescale it properly, but then you can also think of it as having matching moments. So with moment matching condition, and why is that? So because the distributions of, and then if I take this appropriately rescaled sum of x1 up to xn, and I can compare it with the sum of y's, which have the same, and the y's here will have the same moment. So these distributions coincide in the limit when n goes to infinity if the first two moments of xi and yi match. And this, of course, for each I from 1 to n. And yeah, now you don't quite see the yi's yet, but they will appear in the proof, and they will actually be chosen to match, to be Gaussian and to match the xi first and second moment. So, well, yeah, maybe you can look here in the, you'll see it later. I will present the proof here and maybe give some more details in the homework. And there you will see the yi's appearing, and you will actually also see that yeah, we will choose the yi just to match this, to match the first two moments of x, and then we will prove this statement actually where the y is replaced by this sum of the yi's rescaled like this. But this is, again, this is a standard normal variable, and that will conclude the proof. And I guess we will present, I'll present the proof after the break. Okay, then yeah, so, well, then we can continue. And now what I want to present now is a short proof of this theorem 2.3. I'll maybe give a few more details in the exercise session where you were asked to do this step by step. And yeah, the main idea will be that in this sum, we will replace the x1 up to xn step by step by Gaussian random variables, and then in the end, these combinations, if the Gaussian random variables satisfy this condition, then this will be the standard normal Gaussian, the standard Gaussian random variable that we will have here. Okay, so for that so yeah, this is now the proof of theorem 2.3. So we now take Gaussian or normal random variables y1 up to yn, be independent Gaussian random variables such that the following holds. So they have to be independent of the family x1. They're independent of x1 up to xn. They are also centered and they match. So that would be they match the xi's to the first moment because the xi's were centered. The second thing is that I also want the second moment to agree. So I assume that xy squared is the same as yi squared is the same as xi squared, and both of these conditions hold for each I running from 1 up to n. And maybe I should say here, so that these are real Gaussian variables. And then we define we define z's where the sum will be replaced, where the x's will be successively replaced by y's. So we define zi of gamma as follows. So we have two cases. So in the first case it's xi, in the second case it's yi, and the gamma will define when. So if the I is small, I choose an xi, and if the I is big, then I choose a yi. And the I will run from 1 up to n, and the gamma will run from 0 up to little n. Okay, so this is the definition. And now there's an and now I want to rewrite this sum here in such a way that I use the z's, and I replace one by one. I replace those by x's, and let's do this in such an. So I will write it as a sum of these cz's, and this will be a telescoping argument. So telescoping sum argument. To see the following. So what I want to compare is f evaluated at this rescaled sum of the x's, and I want to compare it with the same thing where I have the y's. Okay. And I want to do it in such a way that I use these z's. So this is now this telescoping sum argument. This is used here. So I will sum up all gamma from 1 up to n. You can convince yourself easily that the following is true. So here I first have the sum over the zi gamma. And then I have the same when there's the gamma minus 1. So why is this helpful? Well, so the first thing is that, well, the dangerous thing is, of course, that we now we got a sum, which will in principle make our lives more difficult, because this could give you an n. If you control each sum and here individually, then you will lose an n here in some sense. But on the other hand, these things here will be much more tractable, because these sums here actually only differ in one summand, namely the summand when I is equal to gamma. So for all, whenever I is different from gamma, then these two sums here have the same summand here. And when I is equal to gamma, then this here as well, if you follow the definition, that's xi, while this here is yi. So that's the only place where they differ. And then it's much easier to compare these sums, because to compare this expectation here, because then the argument here is only changed in one place, and then we can use some Taylor expansion to take care of this. Okay. So yeah, I guess I will need some more space. And then we can continue. So I will introduce now the variable w, which we will then use to rewrite the sum a bit, where what I just said verbally, I can make it explicit. So, so this sum there is the same as the sum gamma from 1 up to n. Expectation of f. Now I'll introduce w. I will define it in a second. W of x gamma over root n minus f of w n gamma plus y gamma over root n. And what is the w? where Wn gamma is defined as follows. It's the same sum as before, the sum over the zi's, but then the I zi gamma, but the I is different from n. Okay, and now we're in the situation that you can think of these terms here as being small, so we can compare these two things by using a Taylor approximation for f, and that's what we want to do. That's what we want to do next. So we use the Taylor approximation for f. Around this Wn gamma, and obtain the following. So now we want to estimate each of these terms individually. As I said, we will lose a factor n here, but if the f is sufficiently nice, and because of our moment matching assumption, we will see that this is actually already small. Okay, so we start with this individual guy. So Wn gamma plus x gamma over root n minus the same thing with y. And then, yeah, I use a Taylor expansion. I will not go through all of the details. So first of all, the constant term, of course, vanishes. Then we have the first derivative, x gamma, y gamma, n to the 1/2, plus 1/2 second derivative, gamma cube squared, x gamma squared, y gamma squared, and then we have an error term. Okay. So there is a k, which, because there's a third moment coming in, we have the third derivative of f, which we assume to be bounded, and then, yeah, the x's are rescaled always by this root n. So now I have the cubic guy. So then there's an n to the minus 3/2. Okay. But now, yeah, maybe I should first remark. So yeah, here we used the following things. So we used that the third moment of x is bounded, and one has a similar bound for the y, which comes from the fact that y is Gaussian. So because y is Gaussian, I can control the third moment by the second moment. The second moment to the 3/2. But now the second moment matches the one of x. So squared 3/2. So this is bounded by 3. Well, this is bounded by the third moment of x, and that's bounded by k. And here I use that the yi is Gaussian. So this is essentially, you can see it if you plug in the density, then it's just an integration by parts. And now we can use, so this is here is to estimate the error term. And now we can look at the first place here. So now we can use that the w and the x and the y's are the wn and the x and the y's are independent. So, well, these expectation here factors, but then I see the first moment of x here, so that vanishes, they match, and here I see the second moment of the x's, so this also vanishes by assumption. So so this guy here is actually 0. this here is equal to 0, since so W and gamma, or well, maybe I write like this, X gamma and Y gamma are independent of W and gamma, and X gamma and Y gamma match moments, well, no, the first two moments of those guys match. So the first two moments of X gamma and Y gamma, they match. Okay, so that's why this here is 0. So then if we go back to this here, then we see that each of these summands here, well, maybe it's, so we wanted to estimate this guy here. So by assumption, this here is a standard normal variable. And we now estimated each of these summands is of order n to the minus 3/2. We have n of them, so this whole sum is of order, of this order, where I have to replace this here by, so from this here, we get that this is of order k constants, so to say, stay the same, and I have an n to the minus 1/2, and that's what we wanted to prove. So maybe I write here, from all of this, it follows, the main assertion follows, because if I define y to be this combination, then I get the standard normal variable. Since this is a standard normal random variable. Standard normal. Okay, so yeah, I hope this was now not too messy. I will go through it in a bit more detail in the exercise session. Okay, so now we learned something about this Lindbergh proof, and the main idea was the following. The main idea was that we rewrite the basic things that we want to estimate. So the tested statistics, we write them as a telescopic sum, and then in this telescopic sum, hopefully there's only one term. Well, here it was an individual summand of the sum of the x's. Later it will be an individual entry of the random matrix. So one summand is only different and the rest is fixed. Then we can use a Taylor approximation to reduce it to some question about the moments of this individual summand that was different. And then if the moment match to high enough order, we can make this error term here arbitrarily small. And no matter how many summands we have, if we make this here arbitrarily small, then we can hopefully cancel this sum. Okay, so that's the basic philosophy of this proof. And this we will also see now in the proof of Theorem 2.2. And first of all, today I want to start with giving you some ideas and heuristics about how this proof works. And then maybe we will start a little bit with it, and we'll definitely finish it then next week. Okay, so okay, so maybe I have a section 2.2 here, which is, I first want to give some ideas about the proof of this Theorem 2.2. Okay, and well, if you remember, then our main goal was to show that that I have statistics F of my matrix H, and I have and I have the same statistic of the matrix H prime, and I basically want to show that this is small, and so little of 1 means something that goes to 0 when n goes to infinity, and I have two things. So, well, actually the statistics we have is somewhat clear. Well, maybe I first write, yeah. F of H is some statistics of H. And so, yeah, I mean, here we will have actually F will be the local k-point intensity measure tested against some function. Well, maybe I should. So local k-point intensity measure tested against some nice F. Okay, and the H and the H prime match to order 4. Match to order 4. Okay, and in fact we will not quite use this Lindbergh approach to the original F, but we will use it to something which is which can be rewritten as a green function which can be written in terms of the green function, so that where we can use the local law to control these function. But with such green function with combinations of green functions, we can approximate all these kind of Fs, and yeah, and then this moment matching assumption will come in a similar place as where we used it here. And first I want to motivate why this order 4 is sufficient, and then yeah, I'll talk a bit about the green function. I guess that will be what we'll do for the rest of today. So the idea is again to use this telescoping idea. So use a telescoping sum argument by where we replace the entries of H successively by those of H prime, or vice versa, by successively replacing the entries of H by the corresponding entries of H prime. So that's the same as what we did here. So if you see this in this telescopic sum here, so one by one you replaced all of the x's by y's, and in each summand you had one more. But then these original things, they are somewhat the same, and you just have to control the difference originating from one. Well, here it's from one summand, and here it will be from one entry. Okay, and yeah, as I said before, if we then use in a similar argument, we expand the F in a Taylor series, and the x's and the y's, so which are here the entries of H and H prime, they match up to sufficiently high order, then we can make this arbitrarily small, and then we can control whatever order this sum here has, and here it will be enough to have fourth order. This will come next. So let me write this down, what I just said. if H and H prime match up to arbitrarily high order. So that means if I take a very large order k, where they match, then I can make or little n, then I can make the error term. Then the error from replacing one entry will be arbitrarily small. So that just comes from the Taylor expansion. And yeah, and then we want to choose call this double star. Well, I guess I need some more space. Choose order high. So we want to choose the order then high enough such that in this expansion up there, we get a little O of 1. Okay? So choose order high enough such that double star holds. Okay, and yes, I indicated before. Now I want to look at how high we have to choose this order, and then why the fourth order is correct. So that's the second part here. Why is order 4 sufficient? And well, at least this question, or maybe the more precise question to ask is, why can we expect it, so the fourth order, to be sufficient? Okay, and as before, I now want to one by one replace entries of H by entries of H prime, and to that end, it's easy. It's the most convenient way to do that is to choose a bijection from the set of indices. So I and j. And I have a Hermitian matrix, so I only need to care about the upper triangle of the matrix. So I take I and j where I is smaller than j, and I want to have a bijection to 1 up to gamma n, where gamma n is the number of such pairs. And we can choose just any bijection, so we can fix one arbitrary. Yeah, so we can take an arbitrary bijection, and yeah, I guess you all have already done the computation in your head. So gamma n is of course n times n plus 1 over 2, and that corresponds to the number of independent entries in the Wigner matrix. Number of independent entries of a Wigner matrix. Okay, and now we will have we'll have a whole family of Wigner matrices where the entries are replaced one by one. So I define Wigner matrices starting with H0, which is the matrix H, then H1, and so on up to H gamma n. So these are not powers, but indices of so family of matrices, and they have the following entries. Yeah, as I said before, so that will be H prime, that will be the original H, and I will have the no, it will actually be opposite. That will be H prime. No, sorry. That will be H prime. And I have the following entries. So H gamma ij entry is defined as follows. So Hij prime is it will be Hij prime if the phi of ij is smaller than gamma, and it will be Hij if phi ij is bigger than gamma. Okay, and yeah, this we do for the upper block for I smaller than j, and the gamma runs from 0 up to gamma n. And of course, the other guys we set according to the Hermitian symmetry. So Hji gamma will be Hij gamma bar. Okay, so now we have defined these matrices, and now we can rewrite this here as a telescopic sum in these H gammas. So let's do it as follows. And then the important thing, what will matter is we will have a telescopic sum where we sum over all gamma n, where we have gamma n summons. So that's of order n squared, and that will define us under some assumptions on the F how many moments we need to match. Okay, so then we have the following. So let me see, did I do it correctly? No. So the expectation, so this is the object we want to understand, and now we smuggle in all of the H gammas. So this is the same as the sum gamma from 1 to gamma n, where I take the expectation of the same guy, but now evaluated in H of gamma minus f on H of gamma minus 1. And that's what I want to call 3 star. And now the important thing is that this sum here has n squared terms, or of order n squared. So note gamma n is of order n squared. So this is the number of terms in the sum. And now we will assume that all the derivatives of H of F, so now we will use the Taylor approximation here in this argument. So here we have one term difference, and so one entry is different from when we compare these two matrices. So then we can use the Taylor approximation here for F to arbitrary high order, and we will assume that the derivatives are all bounded, so that only the size of this one term matters. And so that's what I'm saying next. If the derivatives of F are of order 1, then we need 4 matching moments for the right hand side. For the right hand side being little o of 1. Yes, and then in fact, well, at least if you use Taylor's theorem. And here it's important to remember the estimate on the kth moments of a Wigner matrix. So Hij to the k is smaller than some ck n to the minus k over 2. Right? So the point here will be that I do this Taylor approximation, then all derivatives of f will be bounded, and I assume that the moments of this one entry of the Wigner matrix that changed, they have these bound. And then if I do an approximation here to kth order, then this here with k plus 1 will be the first error term. So if I do k equal to 4, then here I have the error term will be of size this expectation to the k plus 1. So I have 5/2, and I multiply this with n squared summons. So this, if I have 4 matching moments, then this will actually be of order n to the minus 1/2. Whereas if I only had 3 matching moments, then here I would have a 4. So here I would have an n to the minus 2. So this would be bounded in that case. And that already suggests as well that that this method is not quite optimal, because of course there are many extra cancellations. There might be extra cancellations here, and if it indicates that at least when I would have 3 matching moments, then this here is bounded. That already indicates that if there's some extra cancellation here, which we don't see by this telescopic sum argument, then that indicates that there might be some improvement. And actually, in the second part of this course, we will see how this comes in. But let me remark what I said here. So maybe I write it like this: H and H prime match to order 3. That would imply that 3 star is of order n to the minus 1/2, order 3, then it's to order 1, whereas they match to order 4. That implies or suggests, it's of course not really a proof, but that this is n to the minus 1/2, so that would be, that's little o of 1. And what we learn also from this is that we have to control the derivatives of f, and need to control the derivatives. Because here we have assumed that they are order 1. Well, if they're worse, then of course we have to make some. Well, and they'll actually turn out to be order 1, but we have to choose the f appropriately, and still this needs some extra argument, some quite non-trivial argument, which will be based on the local law, because in fact we will choose the f to be to be a resolvent because derivatives of resolvents are easier to control, and that will then allow us to apply the local law. But let me motivate to you first why it's good to choose resolvents. So, let me give you some ideas on how to control derivatives of f. So if we apply this sketch that I gave to you before most naively to our situation, then the f looks as follows. So in principle, for this theorem 2.2, we have the following. We have that f is, well, it's not quite correct. There's some rescaling going on, but well, let me write it like this. This is the sum, and then there's some up to rescaling. This is just to motivate what we want to do. So the point here is now, in principle, the f is like a combination of this little f, up to rescaling, and then for some nice little f. And the important here is that it's a function of the eigenvalues. So if I want to control the derivative of this f, then I necessarily have to take care of controlling derivatives of the lambdas. But they are somewhat difficult to control. There are some formulas for those, but that's it's a bit complicated. And you really have to understand how the eigenvectors and these things look like. So that's not so nice. So maybe I remark this first. How to control for such f, we would have to control derivatives of eigenvalues. When I differentiate with respect to entries, because that's what we changed up there. We one by one with respect to derivatives with respect to entries. These are difficult to control. On the other hand, if I use the green function or the resolvent, then this is much better. So on the other hand, derivatives of entries of the green function. For resolvent, we gave the definition last time, maybe just to recall it, because it never harms to see the definition of the resolvent again. These are much easier to control. Are easier to compute. into control. So, well, why is that? So maybe I start with this part here. So if I compute this derivative, I think we've already seen it last semester, then it looks as follows: GIK, GLJ, and the reverse because I have a Hermitian matrix, or, well, maybe real symmetric, ILGKJ. Maybe I want to assume that K is different from L and H is real or something like this. And to control, and so that means that if I compute the derivative of a resolvent entry with respect to an entry of H, then I get back other resolvents. But these kinds of resolvents we can control by the local law. Control by the local law due to the relation that we just proved. Okay, so what is the advantage here of the resolvent of the Green function? So it's twofold. So it's easy to compute. If I compute such derivative, I get back other entries of the resolvent, but those I can control because we have the local law, as we will see later. So that that really much speaks for using the resolvent instead, or the Green function instead of these f's where we have to compute complicated derivatives. But then there is the problem that, well, I want to understand this local intensity, k-point intensity measures. But we have seen last semester that all kinds of all information about eigenvalues and eigenvectors of a Hermitian matrix, they can be recovered from the Green function, and that also works here for the capital F. Namely, we can approximate such a function f by a combination of Green functions and or entries of the Green function, and then we can study those. So we can approximate f by a combination of entries of G. The details we will see later in the proof. And then for the Green function, we can use this Lindbergh approach, which I sketched before. And then the other idea will be, yeah. And then so we can approximate them and then apply a Lindbergh type argument to the Green function. Or well, maybe Green functions of H and H prime, and this method is called Green function comparison. And then, yeah, maybe that will be one very, very important step in the proof, and this we will show next time in lemma 2.4. So let me just recapitulate the ideas that we used here. So we want to study this f, but instead of f to control f directly, because we would have to control derivatives of eigenvalues, we prefer to rewrite f in terms of the resolvent. which should be possible because this is a function of eigenvalues and the resolvent carries all of the information about the eigenvalues. And then finally, for the resolvent, one can use some Lindbergh type argument because this has a very easy form for the derivative, and then the derivatives can be controlled by the local law because the derivative of a green function is again a combination of green functions. And yeah, this is the basic idea. And then next time I will present the proof to you. And yeah, then see you next week on Zoom. And